Go ahead.
Okay, today we'll be presenting on some of our research and work and review on a proposed ISRU flight demo for in-situ air production and solid oxide fuel cells in the Venetian clouds. Next slide. Here's a slide on two habitable biospheres, and notably with toward the bottom of on the left here with Venus, the literature suggests that there's up to 200% less speed around 60 degrees north and south, with around 20 to 40 meters per second wind speeds, or 40 to 78 knots. And so we think this is a good zone for proposed missions here. Next slide, please. And taking a deeper dive into the zonal winds in the atmosphere as a function of habitability. So the research suggests that the velocity is fastest around 65 to 72 kilometers, with peaks here outlined here on the chart on the right. It's observed from the Galileo flyby in 1990, and you can see here that there's a significant drop in zonal wind speeds up closer to the poles, which suggests that there would be less quicker rotations, and would be important for future demos that should help quantify the vertical and horizontal wind speeds and turbulence. Next slide, please. And more about how Reynolds numbers can help us model turbulence, and so it's believed that we'll have around a laminar region of flow at these altitudes, and some important modeling with a momentum equation and equations here for future work. Next slide, please. And so we're also trying to better understand this hydrosulfuric acid and how we can potentially collect water in situ in the atmosphere. And so we know that sulfuric acid is created from the water vapor and can be easily filtered to collect water. But the question is there enough? And so there's over 1% of Earth's water in the clouds at an estimated 48 to 66 kilometers in altitude. And so we can use zeolite filters to adsorb the vapor and also filter out the gases. And so the question becomes, is water is co-located with sulfuric acid, how much more water is in the lower layers and at various altitudes? And so we think that a plasma dielectric barrier, discharge nanoreactor filter, and iron sulfide catalyst and other zeolites could help us ionize and filter the hydrosulfuric acid. Next slide. And so here's more about the proposed ISRU flight demo for in-situ air production. Really a high-level overview to design and test and build this payload and test it here on Earth, and then later for Venus, and really consisting of a pressure swing adsorption unit with zeolite beds, solid oxide fuel cell, and really help decompose the CO2 to oxygen and separate, filter, and store the nitrogen, and whereby we can really begin to create and form this 21% O2 and 78% N2 cabin atmosphere inside the balloon. And then really also help quantify the turbulence or quantify the effects of the other particle species in the atmosphere, such as the hydrosulfuric acid on our subsystems. And with our upcoming Venus Science and Engineering course this summer with Multi-Planet University, we'll be launching and designing and assembling this balloon and launching somewhere in the US, hopefully with our partners, and believe this should be a good next good road for us to help develop our understanding of high altitude balloons and various subsystems. And so, yeah, next slide, please. And here's more about zeolite beads and molecular sieves to filter out particle species. And so these PSA systems, they operate on a 4-step process with adsorption, depressurization, purging, and off-gassing. And it's a well-developed technology, and so we can use CO2 adsorbing zeolites here on the top right diagram and collect and pass nitrogen through the zeolite beads. And so here's more about the crystal structure as well. These molecular sieves inside the beds and the mathematical adsorption process outlined. Next slide, please. And then also another key subsystem in outlining some of the geometry of the scroll pump and how it works with this suction and compression and discharge process, whereby the air is compressed toward the pressure spring adsorption units, and the walls don't actually touch, but they're just compressed with a variable frequency drive motor, which should bring some cost-effective savings. Next slide, please. And so really what we're proposing at the end of the day is something quite similar to MOXIE for Venus, but just tailored ever so toward much higher pressures around 1 atmosphere. And so we've outlined some of the compressor specs here in the table, and we're envisioning a similar subsystem setup here, but to help us collect and adsorb the nitrogen. And yes. And so here's a diagram about how MOXIE works and the flow diagram as well. With the compressor developed from air squared. Next slide. And more about a high-level overview of what we're thinking for the subsystem layout below the balloon. And so we'd have a stowed deflated balloon right here and an inflation system with a pressure hose adapter and fill hose, multiple inlets for redundancy, and really connected to the pressure spring adsorption units and solid oxide fuel cell, and with the power management with inside the electronics control box, and which would also help manage the data command and handling units and systems with algorithms and all sorts of data collection on the flow, valves, air composition, zeolites, fuel cell, the pressures, and really maintain and understand this habitable environment inside the balloon. Next slide, please.
So, Cole, can you move to your conclusions?
Yes, I think it's the last slide coming up. Yeah, we think this is a key life support to support later life clouds, and really provides a good technology roadmap for airlock entry, air breathing, CO2 propulsion, and really all the organics to sustain life and a larger multi-kilowatt in situ air production unit for a human crew. and all sorts of possibilities. So thank you for listening and your time.
Thank you.